Okay, everybody, welcome to my channel. I'm Joe. Today we are going to talk about the algebraic forms of Boolean functions. In general, there are two basic ways or forms to represent the Boolean function. The first is known as sum of product form, or SOP. Okay, in this format, we are kind of collecting add functions with all functions. One example is shown here. So in this Boolean function, like we have some product terms, right? Like a and b bar, c and b bar and c, a bar and b and c bar. We have three product terms here, and we collect them using all function. Okay, and one property you should remember for this format is that the output will be 1 if one of more terms are 1, right? So actually this is a basic property for all function. If one of the variable, or in this case it's not a variable, it's the combination of different variables, but however the term, those variable forms, if they results in 1, then the whole function will be 1, right? Then the second term is called product of sum form. In this case, we are collecting all functions with AND functions, like this example shown here. Okay, we first have three terms that consist of all functions. Then we collect them together using add function. Similarly, the output, in this case, the output will be 0 if one of more terms are 0. Basically, this is a property of AND functions, if you remember, when we talk about the basic logic gates, right? Okay, so those are the two basic forms how we can manage the Boolean functions. But more especially, we have two special formats to represent. One is called standard, or some textbook called canonical SOP form. So this is a special SOP form that contains only mean terms. And the mean term is defined as a product term that contains each of the variables exactly one time in its complement form or truth form. So basically it says in the mean term, every variable in your system should appear and only appear once. But they could appear in their truth form, like itself, or in its complement form, like with a bar or with a prime. Okay. Again, let's look at the example. So in the first example I give here, the SOP form, we can see that the first term has three variables a, b, c, and this is a three variable system. So it contains all of the variables, and each variable appears once. So this is a mini term. And the last term is also a mini term. However, the second term, we can see that it emits variable a, right? So it's not a mini term. Okay. However, if we have a function look like this, all of the three terms contains all the variables just once, either in its truth form or complement form. So all these three terms are mean terms. So this function is represented in canonical or standard SOP form. Similarly, we have standard or canonical POS form. So this is a special POS form that contains only max terms. As contrary to min terms, a max term is defined as a sum term that contains each of the variable exactly one time in complement to or truth form. Okay, so similar idea, but here we just have the sum terms. Still, if we look at this example here, the second term here is missing variable a, so it's not a max term. But the other two terms are max terms. And for this function here, all three terms are max term. So this function is in canonical POS form. Next, let's look at the standard SOP form in more details. This is called standard, means it's suitable for all kinds of Boolean function. For every Boolean function, we can write them in a standard form. Okay, but now let's look more detail about this. There are different ways to write the minterms. So another way we write minterm is that we can use a minterm code or a minterm number. And here is the rule. How do we get the number or code? Okay, say we have a minterm in a 3 variable system, say a and b bar and c. Okay, to get the minterm code, we translate the variable in its true form with 1. But if a variable is in complemented form, we translate it as 0. So a, b bar, c will be translated as 1, 0, 1. That's the minterm code. And 1, 0, 1 equal to decimal 5, right? So the minterm number will use small m with the decimal value, so m5. This another example, so a, b bar, c bar. So after translation, we get 1, 0, 0 as the minterm code, and this corresponding to minterm number as m4. Okay, basically we can write all the minterms in this 3 variable system. So like we start with a bar, b bar, c bar, a bar, b bar, c, a bar, b, c bar, a bar, b, c, a, b bar, c bar, a, b bar, c, a, b, c bar, a, b, c. So those are the 8 possible compilations for a 3 variable system. And if we find out their minterm code, we will get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And the corresponding minterm number would be from M0 to M7. So that's the correspondence of the minterm and the minterm number and the minterm code. So after we have this chart here, we can try to rewrite a Boolean function that using only minterms. We can translate that or rewrite it using the minterm numbers. Okay, so here's how. So first we find the minterm code for each term. So this we got 101, right? This is 100, this is 010. Okay, or you can use this table to find the corresponding minterm number and just collect the minterm number using all function. So this action corresponding to M5, this term corresponding to M4, this term corresponding to M2. So the function can be rewritten as M2 or M4 or M5, or we can use this sigma. In math, we know the sigma represents like plus, but here we can still borrow this idea, even though we don't read plus, we read all, right? So we can power this symbol here. So write as sigma m245. So that's the mean term number we get. But there's one thing I need to remind you that when we are using the mean term list form as shown here, we should know that the order of variables in the functional notation determine the LSB and MSB. So you basically said you can't mess up with the order how you write the variables. For example, here we know FABC has this equal to that, and this equal to M245, and specifically M2 corresponding to A and B bar and C. However, if we can mess the order of variable a little bit, for example, if this time I write FBCA, which means in this case B is the MSB, A is LSB, before A is MSB. LSB. So basically the way you write the F can determine which bit is MSB, which bit is LSB, and that matters. Let's see. So let's say we still have this representation using mean term list form, but when we translate this back to the functional notation, so guess what? So M2 now is not equal to A and B bar and C. Actually, it is equal to, because B is MSB now, so first we have to B should be B bar C A bar. So now M2 corresponding to B bar C A bar, so it's different than before. And M4 should corresponding to B C bar A bar. M5 B C bar A. So just be careful about the order how you put the variables. So this is B bar C A bar, or B C bar A bar, or B C bar A. Okay, you can see they are different functions, but they have the same mean term list form. So you need to be careful about this. Okay, now let's practice a little to learn how we can apply this in the real problem. Okay, say we have another 3 variable system, A, B, C, and we have the functional notation using mean terms only here. So how do we translate this into mean term list form? Again, we need to find the mean term code, then convert to mean term number, right? So this code is 0, 0, 0. This code is 1, 0, 0. Because this is in truth form, we put 1. In complement form, we put 0. Right? So this will be 1, 1, 0, and the last one, 1, 1, 1. So then you can look at the table, but you don't have to. Actually, you just need to convert the 3-bit binary to decimal. Then you will get it. So we will have, so the first term corresponding to M0, second corresponding to M4, third M6, last one M7. So you can also write it as sigma small m 0, 4, 6, 7. Okay, now the second question. So we know f equal to that. Then what about f bar? So the complement of f. The complement, we said basically just the opposite or not, right? So we know in the 3 variable system we have totally 8 mean terms or 8 mean term numbers, and we in original function we have 4 of them. So those are not included will be f bar, right? So we can directly write f bar then is sigma m 1, 2, 3, 5. Then let's put the f and f bar together. What do we get? So basically we get, even though we get sigma m 0, 1, 2, 3, 4, 5, 6, 7. Right? Basically, this is every term shows it here. So every possible term will be included if we put f plus f bar. And what does that mean? This means no matter what value we give to the three variables, any value in this list, the output always be 1. So this result always 1, because there's always one term that gives you 1 there, and everything is collected using all function. If one term is 1, the function is 1. So if we do that, you always get 1. Actually, this is already proved when we're talking about the Boolean theorem. If you don't remember, you can go back to that lecture, and I think you should look at which one is that? Okay, look at the theorem 2-8. So basically it says x or x prime equal to 1. Right? If you take this as x, this would be x prime. In a similar way, let's talk about the standard POS form. Okay, just like the SOP form, each standard POS form term can be represented using a max term code or max term number. But the rule is a little different. So in order to write max term code, we need to translate to 0 if we see a variable in true form, and write 1 if the variable is in complemented form. This is opposite as SOP. Just be careful about that. So like A or B or C, we should translate it as 0, 0, 0. Okay, and corresponding to, now we use big M to stand for max term. So big M 0. Then A, B bar, C would be large M2. A bar or B bar or C will be large M7. Again, let's write all the max terms and their corresponding code and number. So we can start from A or B or C, A or B or C prime, or C bar, A or B prime or C, A or B prime or C prime, A prime or B or C, A prime or B or C prime, A prime or B prime or C, finally A prime or B prime or C prime. And this will be translated to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So they are corresponding to big M0 to 7. Okay, so now we can also rewrite the Boolean function using max term, something called a max term list form. So to do that, we still try to find the max term code for each term here, each sum term here. So A or B or C, that's 0, 0, 0. This is 0, 1, 1, and 1, 1, 1. If you find the decimal value for these three numbers, we got 0, 3, and 7. Okay, then this function will be rewritten as this: big M0 and big M2 and big M7, or we can borrow the Greek letter pi here, which stands for the multiply. Okay, but here we borrow that, even though we don't read the multiply, we read the add, right? So this is pi big M 0 to 7. Okay, let's also try some practice on max terms or POS form. So in order to translate the functional notation to max term list notation, so first find the max term code. Okay? So this we got 1 1 1 0 1 1 0 0 1 0 0 0. Okay, just be careful. This time, when the variable is in true form, we put 0. In complemented form, we put 1. Opposite as midterm. So find the decimal value here. We got 7310. So we can write this as pi big M 0137. Or you can write it as M0 and M1 and M3 and M7. So again, if you want to find the complement of that function, basically that this thing is not included in the original function. So we can directly write as pi big M 2, 4, 5, 6 in this case. Finally, what happens if we multiply f and f bar together? So we will see that it's basically multiply everything together, right? 3, 4, 5, 6, 7. And what's the result of this? So again, like no matter which value you assign to A, B, and C, what do you will get? So one of the terms will be 0, right? No matter what value you assign, there are some terms to equal to 0 in this function. And because each term are collected using add function, if one term is 0, the whole function is 0. Again, you can find this in the theorem list 2-8d. Which says that x and x prime equal to what? 0, always. Now we know the difference between miniterms and max terms, but do they have some sort of relationship here? So let's find out in this slide. Say we have an example function here, which equal to z. Let's write this into, because this function is composed of max terms, right? So let's try to rewrite this using our max term list form. So this will equal to big M. So we got 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. So basically we have big M 1, 3, 5, and 7. Okay, now let's do something different than before. Let's calculate f prime, the complement. So we already know that this can be written as big M 2, 4, starting from 0. So 0, 2, 4, 6, right? But however, let's do it using another way. So we do it by applying the De Morgan theorem. So what we do is we put a bar over the whole thing, so you get this. Right? So yeah, maybe I unify the way I write it. Since I use bar here, so I will do the bar here. Okay, now let's apply De Morgan theorem. If you remember what De Morgan theorem says, we can rewrite this function into this, the bar here, or so and become or. The true form become complement form become true form, right? got this. Then if we apply De Morgan's theorem again, what do we get for each term? So for the first term, I will get something like a bar, b bar, c. The second term, I will get a bar, b, c. The third term, I will get a, b bar, c. The last term, I get a and b and c. Then if we write this in using mean term list form, we will get sigma small m, what's that, 0, 0, 1, 1, 0, 0, oh sorry, 0, 1, 1, 3, 1, 0, 1, 5, 1, 1, 1, 7. Okay, so we find f bar actually equal to that. And we also know that f should equal to f bar bar. Also, this comes from the law of involution, right? So if we take another bar for this, which means that the bar of f bar we know equal to m 0, 2, 4, 6, right? So this should equal to pi m 1, 3, 5, 7. So what we found? This really tells us for a given Boolean expression, if we know the mean term list form, we can directly write down the max term list form too, using the term not included, using the numbers not included in the mean term list form, and vice versa. So understand the property of mean term and the max term and their relation is very helpful, especially when we are trying to figure out the truth table of a digital system. Okay. For example, if I know a system, the output can be represented using an expression like this. How do I generate the truth table quickly so I know how the system actually perform, right? So here I'll show you how to do this. But first, let's start with analysis. So let's first write this mean term list form back to using variables. So 0 corresponding to a prime, b prime, c prime. Okay. And the 1 refer to a prime, b prime, c. 5 is a, b prime, c. So this is how we write the mean term list form back to the functional notation using variables. Okay. So if you remember the property for all function, right? In order to make this function equal to 1, what should be satisfied? We know that one of this term has to be 1, right? So if we look at the first term here, when will this term be 1? As we already know that from the property of NAT function, a has to be 0 here, b has to be 0, and c has to be 0 at the same time. Then this term will be 1. So, and if this term is 1, f is 1, right? But also we have another option to make if this term is 1, f is also 1. Then how to make this term to be 1? We got a equal to 0, b equal to 0, and c should equal to 1. If we have this being satisfied, then f also be 1. Also, we have the third choice, which is a for this term. A should equal to 1, b should equal to 0, and c equal to 1. If this is satisfied, the f is also be 1. Then this thing is easy. We just go to the truth table, look at the input combination to find the corresponding combination and put the value 1 there. So the first one, 0, 0, 0. So this should be 1. F 0, 0, 1. This should be 1. 1, 0, 1. This should be 1. Now how are the others? The They are not 1, so they has to be 0. So use this way we can quickly fill out the truth table. But we can make this even quicker. So if you notice the combination here, those input combinations actually correspond to the mean-term numbers, right? So this is M0, this one is M1, this one is M5. So now we can summarize this. If we know a function in mean-term list form, in order to fill out the truth table, we just find out the corresponding mean-term number, right? Put the output to be 1 there. And for the rest, fill 0. So this is very quick. So this is a very quick way to figure out the truth table for a given function. Now let's apply what we have learned to a problem like this. Now we have a 4 variable system. First you need to think about, for the 4 variable system, we should have 2 to the power of 4 equal to 16 possible combinations of the input variables, right? So in this truth table, we should have 16 lines to fill. So this function is given in the mean-term list form. So apply what we have learned in the previous slide. All we have to do is find the corresponding mean term, then fill the output with 1. So if we write the m term in this column here, so it's 0, 1, 2, 3, 4, 5, 6, 7. How do I figure out this number? You just check the decimal value of the input combination. Right? So we got 8, 9, 10, 11, 12, 13, 14, 15. All we have to do is find 0, 2, 3, 7, 12, 13, 15. And put the output value to be 1 in those locations. The rest we just fill zeros. So you can see this is very efficient and very quick. And this is just an add up. So some of you may wonder what happens if the function is not given in the standard SOP form or canonical SOP form. What happens if we have long mean term there? So in this case, we need using similar analysis as we shown before. So we first think how to make this function to be equal to 1. Right? Again, from what we have learned, we know that the f will be 1 when a equal to 1 and c equal to 1, or b equal to 1, c equal to 0. This is corresponding to the second term. Right? Even though they are not mean terms, but we can do similar analysis. Then what we do is go back to your truth table here, looking for the corresponding combination, input combination. So a equal to 1, c equal to 1, where are they? Here and here, right? A and c. We only look at a and c, so put them to be 1. And for the second one, b equal to 1, c equal to 0. So looking for where b equal to 1, c equal to 0. Put them 1. Then for the others, just put 0. So you can still do it. Then how about max terms? If we have function in max term list form, how do we fill the truth table? So similar, but a little different. Again, let's try to understand how to do the analysis, then we know how to fill. First, let me rewrite this function using variables. So this is in max term list form. So big M0, which corresponding to A or B or C, right? 1 corresponding to A or B or C prime, 5 corresponding to A prime or B or C prime. Okay, then let's think question. Because this is add function here, so we need to think how to make f equal to 0, not 1 this time. We found if one of this term to be 0, then the whole function will be 0, right? So we start from the first term. So how to make the first term to be 0? Then we need a equal to 0, b equal to 0, and c equal to 0. Or if we look at the second term, a has to be 0, b has to be 0, and c has to be 1. Or if we look at the third term, a has to be 1, b has to be 0, and c has to be 0 to make it 0. Then we just go back to the truth table, find the corresponding combination, put 0 there. So 0, 0, 0 should be 0, 0, 0, 1 should be 0, 1, 0, 0 should be 0, then the others must be 1s. And again, if you look at those combinations closely, find their decimal value, basically they are corresponding to the max term numbers. So 0, 1, 5, right? Oh, sorry, I think I made a mistake again. So 5 is here. So then we can summarize again. So if a function is given in max term list form, to fill out the truth table, we need to find out the corresponding combination for the max terms and fill 0 for the output there, and fill 1s for the rest places, right? Then how about functions not in the standard POS form? Like we have long max terms, right? Similar. You just figure out when the f has to be 0. So this will happen when a equal to 0 and c equal to 0, or b equal to 0 and c equal to 1. Then you just go to your table, find the combination. A is 0, C is 0, put 0. And here also put 0. Also B equal to 0, C equal to 1, put 0, 0, 1, 0. Then the rest would be 1s. Okay, finally, let's talk about the truth table with incomplete specified function, or in some textbook called don't care functions, don't care values. Okay. So here, what is don't care states or don't care value? So in some digital systems, certain combination of the inputs may never happen. Those type of circuit exist, like some input value, we never see them, or even we see them, their value doesn't matter because they won't affect what we want from the circuit. And those combinations we call don't care states. Okay. And in a more official term, we call those functions incompletely specified functions. Okay. So here is an example with don't care states. So the don't care states is is filled with x. So basically x means we're not sure, or we don't care what's value there. Could be 0, could be 1, doesn't matter. Okay, then we need to talk about how do we write the Boolean function in min-term list form and max-term list form for this. So basically what we do is, let's start with min-terms. So f Here we need to do the opposite. Before I showed you how to translate from function to truth table. Here we do the opposite, but the idea is the same, because we know that wherever the f equal to 1, they're corresponding to a mean term, right? We just need to find the mean term number of those ones. We got 0, 3, and 7. So we first have the mean term 0, 3, 7. Then we put all function with the don't care state, and the don't care state in mean term list we use small d to represent it. And we know the don't care state happens at m1 and 6. Then that's how we write it. For the max term list form, similar way, because we know each 0 corresponding to a max term, right? So we find out the max term number for those zeros, which is big M, 2, 3, 2, 4, 5. This time we need to add the don't care state because it could be 0, right? The don't care state can be 0. If they are 0, we just add them together, which 1, 6. Okay, so that's how we do it. Okay, so that's for today's lecture. If you think my lecture is helpful, please help like, share, and subscribe. See you next time.